In this episode, I'm going to talk about strictly competitive games and zero-sum games. Both of those concepts will be defined for two players. So in this episode, we're going to be looking at games where there are two players, and we will also be looking at or talking about games where there are finitely many strategies for each player. Well, zero-sum games are a subset of strictly competitive games. So what do we mean by a strictly competitive game? Well, a two-person or two-player strictly competitive game is such that for any two strategy profile S prime, pure strategy profiles, if player one prefers strategy profile S over S prime, well then that means player two prefers a strategy profile S prime over S, meaning players' preferences over outcomes are opposite of each other. All right, so the best outcome for player one is the worst outcome for player two, and so on. All right, so that's the idea. Well, as I said, zero-sum games are a subset of strictly competitive games, and a game is called zero-sum game if for any strategy profile, when you add up players' payoffs, you're going to end up same constant, C, and that has to be true for every strategy profile, but we just normalize this constant to zero. All right? So standard examples like rock, paper, scissors game, where you either win or lose or there's a tie. Or a matching pennies game, again, you win or lose. If you win, you get +1, and if you lose, you get -1, kind of. So these are sort of a symmetric zero-sum games. This is also a zero-sum game, but it's not symmetric. The key thing is that whenever you add up players' payoffs, for every strategy profile, you're going to get the same constant, which is 0. So 2 minus 2, 0, minus 3 plus 3, 0, and so on. Okay? Well, you may wonder why we are looking at zero-sum games. Actually, this is kind of the first game analyzed by John von Neumann, which is sort of the father of game theory. So he mathematically defines game theory, or strategic form games, and then he describes a solution concept for zero-sum games. Well, why zero-sum games but not for all games? Well, probably the idea is that the zero-sum, at least the solution concept that I am going to describe in a minute makes much more sense when we talk about zero-sum games, because in a zero-sum game, one player's gain is the other player's loss. All right? So, here's an important concept, a Maximin strategy or Maximin payoff. A mixed strategy, sigma I star, for player I, is called a Maximin strategy if it solves this optimization problem. I'm going to come to this optimization problem in a minute, but sometimes the Maximin strategy is also called security strategy, especially if the strategy solving this optimization problem is a pure strategy. All right? Well, in order to visualize what the heck this optimization problem is, I want to use a simple example. And so I'm going to focus only on the pure strategies, all right? Not the mixed strategies. The mixed strategies is making this optimization problem more general, obviously. But let's for now focus on the pure strategies. So here, what is the first part? The minimize this utility function by choosing sigma minus I. All right, so the idea is basically the following. Player I is asking, well, by the way, whenever you see I, if it is going to make your life easier, you can say I is equal to 1. So therefore, what is minus I? Well, it's 2, because there are two players. Or alternatively, I can be 2, in which case minus I is player 1. Okay? So, but I'm going to keep using I because, whether it's player 1 or 2, the arguments are going to be the same. So the player I looks at this game and asks the following question. If I play sigma I, what is the worst payoff I can get? All right, so he's kind of a pessimistic guy, and he's looking at the worst things that could happen to him, and so he's trying to minimize sort of the loss, all right, by maximizing the payoff. Well, Well, if I play sigma I, so for example, in this case, in this game, if I play A, all right, it's a pure strategy, yes, I know, but for simplicity, stick to it. So if I play A, what is the worst payoff I can get? Well, obviously I can get -2 or 3, all right? Or if my opponent is playing some mixed strategy, anything in between these two, but the worst thing I can get is -2, all right? So if I play A, the worst payoff I'm gonna get is -2. But, you know, A is not my only strategy. I also have other strategies like B. If I play B, what is the worst thing I can get? Well, obviously the worst thing I am sorry. That's my mistake. I am a player 1. All right. So as a player 1, I am asking, if I play A, what is the worst payoff I can get? It's not -2 because it's the second player's payoffs. So I can get 2 or -3. I am sorry. So the worst payoff I can get is -3. However, if I play B, what is the worst thing I can get? It's either 0 or 1. So the worst thing I can get is 0. Good. So the question is, the least amount of payoff I can guarantee for myself or secure for myself is 0 in this game. And I can guarantee this payoff by playing B. All right. So therefore, if we restrict our attention to pure strategies, B is the Maximin strategy, and my Maximin value is 0. Because if I play B, all right, the worst thing that could happen to me is 0. Right? Whether my opponent is rational, irrational, I don't know, I don't care. I don't know what he's going to choose. But, right, I mean, if I choose B, the worst thing I'm going to get is 0. Maybe I'm going to get 1, I don't know, but I'm looking at the worst thing possible. So in this game, again, I can get higher payoff, but the worst thing is 0. But if I do not play my Maximin strategy, for example, if I play A, well, I may get something better than 0, 2, all right, if I'm lucky, but I may actually get something much worse, -3. So again, so this is sort of a pessimistic guy who is trying to minimize the loss he's going to suffer. And so the Maximin strategy is the security strategy, quote unquote, that secures the lowest payoff he can ensure for himself. All right? And so this is what this optimization problem is. Your opponent, given that you're choosing sigma I, your opponent is minimizing your payoff by choosing sigma -I. Well, then the question is, what strategy is going to sort of the minimize that loss, okay? So what I would like to underline is the following. So again, yes, we did not look at mixed strategies here, but in fact, we don't really have to look at mixed strategies all the time, because this sort of optimization problem is equivalent to this one: maximize sigma I element of sigma I, capital sigma I, minimize S minus I element of S minus I, UI sigma I S minus I. What does that mean? That means the following. A mixed strategy is Maximin strategy if it solves this or if it solves this. They are equivalent. Okay? Well, why is that so? Well, kind of simple, because, well, first off, what is the difference? Well, as you may hear, I am trying to minimize this payoff function over all the mixed strategies that my opponent may be choosing. Here, I am minimizing this payoff over all the pure strategies that my opponent may be picking. So here, I am trying to minimize it over a larger set. Here, I am minimizing this payoff over a smaller set. But they're equal, meaning it doesn't really matter. Well, why is that so? Well, because remember, these are expected utilities, all right? So the expected utility function, if you remember the functional form of the expected utility, it's linear on my opponent's mixed strategy, or the sort of the probabilities of my opponents playing A and B. So in that sense, for example, here I may get 2 if my opponent is playing A, I may get -3 if my opponent is playing B, or I may get something in between 2 and 3 if my opponent is playing a mixed strategy. But I know that the worst I can get here is when my opponent chooses B, the pure strategy. So when my utility function is linear on my opponent's mixed strategy, at least when there are 2 strategy, it's linear. When there are more than 2 strategies, we don't call it linear, but the thing is, the optimization problem will always give us the boundary solution, meaning the pure strategy is going to be giving us the minimum, not a mixed one. So therefore, whether you're minimizing over all mixed strategies or over all pure strategies makes no difference. However, maximizing over mixed strategies versus maximizing over pure strategies makes difference because, you know, once we did the minimization, this problem is no longer linear, all right? And so maximizing over pure or mixed strategies is going to make a lot of difference, all right? Well, why do I mention this? Well, because we are going to use this description of Maximin strategies and Maximin value when we solve numerical examples. It makes life easier, okay? So we are sort of a few steps before our first solution concept. So this idea of Maximin is a good idea for for any games, right? Because it basically tells me that whatever my opponent is doing, that is the least amount of payoff I can secure myself. Well, but the thing is, so what does that mean? That means player 1 and both player 1 and 2 are going to think the same way, right? So player 1 is going to solve this problem, maximize sigma 1, minimize sigma 2, u1, sigma 1, sigma 2, right? And then player 2 is going to do the same thing. His Maximin strategies maximize sigma 2, minimize sigma 1, right? Here I am using the second player, utility of player 2, sigma 1, sigma 2. Okay, so both players are going to choose their Maximin strategies, probably. But the thing is, can this be the solution of this game? Well, I don't know, maybe. So here's one thing that we can observe. Remember, this is a zero-sum game. So for any strategy profile, we know that the sum of the utilities is equal to 0, and so whether this is a pure or mixed strategies doesn't matter. It will also give me the same, once you fix the mixed strategies, the sum of those payoffs, expected payoffs, will also be 0. So what does that mean? That means, for example, let's use this one, u2 sigma 1 sigma 2 is equal to minus u1 sigma 1 sigma 2, right? So we can write that. So instead of u2, right, this is the second player's optimization problem in a sense, I can write minus u1 sigma 1 sigma 2. So what is the second player's optimization problem? Maximize, minimize payoff of the minus of the payoff of first player. But you know what? I can take this minus outside of this minimum, but minimizing a negative of some function means negative of the maximum, right? I mean, so here's the thing. So let's say this is the function that this is my u function, u1, and this is minus u1, okay? So this is 0. So what happens is that I would like to let's do it this way, because now I can minimize it. I'm sorry. So this is u1, this is minus u1. So I would like to minimize this u1. So this is the minimizing, and this is the minimum value. But as you can see, this is the maximum value of u1, right? So therefore, I can write this as minus of max sigma 1, u1, oops, I don't need this parentheses, u1 sigma 1 sigma 2. Okay, so Well, once again, once you try to maximize a negative something, it basically means you can pull this negative out, but it's going to make this max min. So this entire thing is the minus of min sigma 2 max sigma 1 u1 sigma 1 sigma 2. Okay? So, all right, well, the nice thing is that, so this is one optimization problem player 1 will be solving. Player 2 is solving a similar problem, sort of implies this one, all right, this optimization problem. So you know what, they're not the same thing, obviously, because here I first minimize and then maximize. Here I first maximize and then minimize. So what John von Neumann defines is what we call a minimax payoff. And then he shows that the min-max payoff, or the value, and the max-min value in zero-sum games must be equal, and he calls this as the value of the game. And so this is the solution concept that he has. So let's describe the minimax value next. All right, so the minimax utility level is the worst expected utility or payoff a player can be forced to receive if he responds the rival's action optimally. All right, so here what happens is that given that my opponent is playing sigma minus I, what is my best reaction? All right, so if you look at this, for example, if my opponent is playing A, what is my best reaction? What strategy maximizes my payoff? It's obviously A, right? So the payoff I'm going to get is 2 by playing A. Well, if opponent is playing A. Well, if my opponent is playing B, however, what is the best payoff I can get? It's 1. Right? So it's either 2 and here 1. Well, the thing is, my opponent is trying to minimize this. Well, I mean, you may say that why my opponent is trying to minimizing my payoff here and here. So that's the beauty of zero-sum games. If I try to maximize my payoff, it means I actually try to minimize my opponent's payoff. All right, so for that reason, this max-min idea makes a lot more sense in zero-sum games. We cannot say the same thing for non-zero games. So probably this is why von Neumann sort of studied on zero-sum games. So, well, my opponent, how can he minimize it? Well, if he plays A, I'm going to get 2. If he plays B, I'm going to get 1. So therefore, if he tries to maximize his payoff, he should be minimizing my payoff. So the minimum he can give me is 1. So my min-max utility level is 1. Again, here remember my max-min utility level was 0. But don't forget, we were looking at pure strategies only. So those descriptions are not given for mixed strategies for no reason. There's a lot reason why we're talking about mixed strategies here. But when it's just to visualize what the heck these optimization problems are doing, focus on the pure strategies. So the minimax value is going to be 1 here. Okay? Again, if we concentrate on pure strategies only. I will solve these problems next for mixed strategies, but before that I would like to underline the following equivalence. So this problem is equivalent to this one. Minimize sigma minus I element of capital sigma minus I and maximize Si an element of Si ui sigma Si sigma minus I. So we don't really need to maximize overall mixed strategies because this function, this expected utility is linear on sigma I. So the maximum value will always be on the boundaries. But so for that reason, you don't really have to worry about mixed strategies. Just look at the pure strategies. That's important, that this equivalence is important because in the numerical example, we're going to use this version, not this one. Once I maximize it, this payoff is no longer, this utility is no longer linear, and so this minimization has to be done over mixed strategies. All right, but this is how we find the min-max utility levels.